Lesson 1.4 is hopefully going to be some review for us from Algebra 1, and that's going to be working on solving equations. We have all the properties of equality and, again, more properties of equality listed at the top here that's going to allow us to solve those equations, and hopefully a lot of these are going to be a review. Especially with the second section when we're doing those operations, adding, subtracting, multiplying, dividing from both sides. That's going to be, again, kind of the goal to isolate for our variables here, again, kind of given by the description, which you guys can read in this next section. About how we're going to actually get those isolated. And again, hopefully you guys have seen this before, and we're just kind of recapping how we're going to do that. So when you start in Algebra 1, you start with one-step equations when you're starting to isolate for a variable. And that means, again, if we're going to use these inverse operations, we're looking at the opposite of whatever operation we start with. In this case, x plus 7 is going to be starting with addition. And we're going to use the inverse operation, so in this case subtraction, to take away that 7 from both sides. Again, we do want to do that operation to both sides to keep that equation in balance according to my property. And that way we're going to have x isolate on the left-hand side, again 7 minus 7 making 0, and negative 13 minus 7, being careful with our integers here, we get negative 20. All we have to do to isolate is to get x by itself. It looks like we've done that, and that means we've just solved that one-step equation. Again, a solution in the equation is just going to make that equation true. If I was to substitute negative 20 back into your equation, which is always a good idea to check your answers, negative 20 plus 7 does indeed give us negative 13. So a good one to try, again, one-step equation right next to it, 6b is equal to 8. See if you know what operation is going to undo that. And that operation should be division, again, because you're thinking inverse, opposite of multiplication there being division, just divide both sides by 6. You do want to make sure you simplify your fraction, so if I get 8 over 6 as a first answer, I do want to simplify that answer to be 4/3. 4/3 being most commonly seen on something like a standardized test, you're going to see that simplified fraction. So if I was instead solving a multi-step equation, you're just having to do the same thing, just going to do a couple more steps, again, multi-step rather than one step. One thing we want to see here is if I have a variable on both sides, we do want to isolate that variable on just one side. Again, notice how we don't have like x and then x on both sides of a solution. In this case, you have a choice. I always choose to keep my variable coefficient positive. Just makes it a little bit easier for me to read, but again, it's up to you in terms of where you want to isolate that variable. In this case, if I add 2g to both sides, again, that being the inverse of that negative 2g or minus 2g from the original, that's going to undo that negative and move that, or rather cancel that right-hand term, and then our left-hand term becomes a positive 1g, again with negative 1 plus 2 being that 1 as a coefficient. And then again, multi-step, just because I have to take one more step using those same inverse operations. My goal is always to isolate the variable, so notice I'm not subtracting 23 from both sides. I want to isolate the g, so if I want to get rid of that 15, I'm subtracting 15 instead, and that's where I have my variable now by itself, and 23 minus 15 on the other side, now making 8 for my solution. Again, multiple steps could just be a little bit different in terms of my properties. So in this case, it looks like we're going to have to start with a distributive property. We do want to simplify a side down first and get it into its simplest form before we start moving anything over with our inverse operations. So let's make sure we distribute that negative 3. You do want to make sure you're including that negative. If you only multiply by 3, oftentimes people forget that second term is going to change signs as well. So the first term is going to stay the same, still just have a 2. But if I multiply negative 3 times x, I get negative 3x. Negative 3 times 4 is going to make that negative 12. And again, 8 is going to be on the other side of the equation with nothing being done to that yet. I'm going to continue this equation up on the top right here. Again, noting that we still need to simplify that left-hand side by combining like terms. 2 minus 12, making that a negative 10. We do want to remember that the coefficient for x is negative 3. And then if I take a step to add 10 to both sides, I get negative 3x to be 18. And then to take one more step and divide by negative 3. Again, all just using my inverse operations. Opposite, even though this looks like it's a minus, again, remember it's negative 3 times x. It's not x minus 3. We want to use that opposite of multiplication, which is division. And now I've isolated that as negative 6. Again, remembering that a positive divided by a negative is going to make that into a negative value. So trying that question underneath by yourself, let's reveal that solution. There we go. Again, distributive property to start, subtract 8 on both sides, divide both sides by 2, and that means that 0 could in fact be a solution. You don't want to think that 0 means that there's no solution. If I was to substitute 0 back into that original equation, I get 0 plus 4, that makes 4, multiply that by 2, I get 8. Looks like it does keep that equation balanced, it does keep that equation true. So next we have our classic bus problem where two buses are leaving in opposite directions, and we want to measure if they're going in two opposite directions at those different speeds, when they're going to be a total of 400 miles apart. It's important to understand what we're answering for first. If it's a when question, that's going to be, again, a matter of hours here in terms of a time, how far they're 400 miles apart. So let's define that for our variable first. You can use anything really for time, but let's just call that x. X is going to be the number of hours that they're traveling. So a number of hours because they're going miles per hour, not something like meters per second if I want to use a different measurement of time. But if I'm leaving from the same place in opposite directions, I think it's always good to have like a little diagram drawn for yourself so you can understand the question a little bit better. If they're both leaving in Houston, driving different ways. The way I'm going to represent the distance is rate times time. So if that's 55 miles an hour for my rate times the x that we don't know for one direction, and 45 miles per hour times the x that we don't know for the other direction, that's going to give us a total, again, of 400 miles at some unknown time that we have to solve for. So I think that's probably the hardest part of this problem is really understanding how to set this up. Once we have this into equation, it's much simpler. But again, if I can just add those two together, so 55x plus 45x, that's just representing the distance that the first bus and then the second bus travels. If I just add those two distances together because they're traveling in direct opposite directions, I'm going to have that total of 400 being at that time that we haven't decided on yet. So now that I have that equation, it looks pretty simple. Just got to add those like terms together on the left-hand side and then take one more step to divide both sides by 100 using my division property. And I get that x is going to be 4. Again, that's what I need to figure out from this question is the number of hours. So I just want to put those units on for a nice word problem answer. And that's going to be 4 hours in which they're going to be 400 miles apart. Again, if you're not sure on these types of questions, you could always substitute your answer back in. 4 times 55 is going to give you the distance that the first bus travels. 4 times 45 gives you the distance that the second bus travels. And if your equation is in fact true, those should both add up to 400 if you're looking for the sum of those two distances. So it works as well with different kinds of questions. We have an example of a perimeter question, which we might see from geometry. We're given a few different measurements, so let's see if we can find out our solution, which you guys might have come up with. This is a perimeter question, so we need to make sure we know, first of all, the way that we're going to find perimeter. We need to keep track of the length and the width because I listed that formula for the perimeter is twice the length plus twice the width, or you could also just think of just like adding all those sides together. Perimeter, again, different from area. We're not looking for the area within this rectangle. We're looking for the distance around those sides. So if I'm told that it doesn't really matter which one's which, but let's say the length from that figure is 3x, the width being just x by itself. If we need a total perimeter of 200, again, given from the question itself, that means I just need to set up that perimeter equation, twice the length plus twice the width, twice the length plus twice the width. I want to plug back in the expressions for the length and the width, which we know. Again, so far, just in terms of the variable expression, we know the perimeter is 200. So really, the equation that we're looking to solve with our algebra steps is 200 is equal to 6x plus 2x after I've multiplied both of those by 2. So 2 times the length, 2 times the width. That's where I got that 6 and that 2 from for 2x and 6x. But then, again, just got to make sure we combine like terms. That way we get 8x. Divide both sides by 8, and we get that x is 25. We do want to be careful here, though. We want to make sure we're answering the question. If the question is looking for at the end, what are the dimensions of the flower carpet and not just our variable for x, we do want to make sure we substitute that back in for our expressions for the length and the width. Our expression for the length was 3x, so 3 times 25. That gives us 75 meters for the length. And our width was as simple as just saying that's the same thing as x. So if x was already 25, we know that our width is just also going to be 25 meters. So we might have solutions which, again, might have equations rather, which either have no solution or we might have equations that are always true. In that case, we'd call those identities. So again, 2 additional cases we might need to consider. So if we have to find out if an equation is always true, that's going to be something we call an identity. If it's sometimes true, we've seen those examples before, something with just a definite solution like x equals 25. If it's never true, that's just another way of saying that that equation is going to have no solution. So let's examine an equation like this, where if I go through my steps, again, just going to start like usual, combining like terms. Want to make sure we simplify both sides, 3x plus 6. Simplify this side, we get 3x plus 4. We might already begin to see a problem. If you don't see it, you can still continue trying to solve. Again, usually our step is to try to isolate x on one side or the other. But if we find out that we've eliminated our x variable completely and we end up with a statement like 6 equals 4, we know that that's never going to be true. 6, no matter what, is never going to be the same value as 4. So this would be either no solution, or you could say this is an equation that's never going to be true. Because again, if x has been canceled, and even if I was to substitute any value back into the original equation, we're never going to come up with an answer that's going to work. So let's try that again just by using a couple different steps. First step here being to distribute 2x plus 3x and then minus 12, again making sure to multiply twice, and then 4x minus 12 plus x. If I use my distributive property, next step is to combine like terms, 5x minus 12, and I get another 5x minus 12. You guys might notice something on this step here, but again, let's say if we don't catch anything, I can still try to isolate for x. If I eliminate x completely this time, and if I notice that I'm left with an equation that is always true, again, this time I know that negative 12 is always equal to negative 12, I can say the equation is always true. This would be also an example of what we call an identity. So an identity being an equation that, again, is always going to hold true for no matter what value we use for x. I could plug anything back into that original, always going to be true for both sides. So if we try that a third time, again, go ahead and give that one a shot before we reveal it, but here's our answer. Again, want to make sure we combine like terms on our first step. Again, we can already kind of see something going on in that very first simplification. We have the same exact expression on both sides. That's going to mean that even if I isolate for x, or sorry, cancel it rather, I find I get an equation that's always true. Again, if I have an equality when I'm done that's true, that's going to be always true for my equation. If I have an equality at the end that's a false equality, I know that's never going to be true for no matter what variable I use for, what variable or what value I use for x to begin with. So last we have solving literal equations. Literal is in we want to solve an equation that is basically just going to stay an equation once we're done solving it. So if I'm asked a question like this, what is c in terms of k? Essentially what that's saying is we want to isolate c, but if I say that it's in terms of k, that means that k is still going to end up in my solution. Unlike our questions from before where I just had like a definite answer, like x is going to be equal to 25. In this case, we're going to find that if I take that equation, k equals c plus 273, if I want to find c, that means I still want to isolate it. So let's use our inverse operations, take away 273 from both sides. I get that c is equal to k minus 273. Again, this is my Celsius Kelvin conversion. And I know that if Celsius is equal to k minus 273, notice I can't really do anything with that k. That just means that my equation is solved in terms of k, meaning that I still have a variable left in that expression. But that's fine because, again, we've isolated for c. That was our job, is to get that basically rewritten in a way that has c on one side and nothing else. So I can do that also with Celsius and Fahrenheit. We have our conversion given from that equation up above. Again, if I ask a question like what is c in terms of f, that means you want to isolate for that variable f. But in terms of c means that c could still remain on that right-hand side of our equation or other side of the equation rather than f. And if I solve that equation, that means that, again, probably the easiest step, a lot of people might look at this and look at distributive property, but it's a little bit easier here if we instead multiply both sides by a reciprocal, multiply both sides by 9 over 5. That's going to directly cancel my fraction, so I don't have to do anything with distribution. And then on the second step, pretty easy, all I got to do is add 32 to both sides. And now if I see that f has been isolated, but again, it is in terms of c, meaning that c is still a part of that expression. It's not just simply numerical values. I do still have a variable left on that other side, not next to the f. I have solved for f. It's just going to remain my answer in terms of c, as in c is part of that solution on that other side. So a literal equation, again, you're still going to have a variable in your solution, but if I've isolated for the one that we're looking for, we've isolated for f, we've still left that in terms of c because c still appears in that equation.